I'm Hongmin Zhou from Beijing Normal University, and I'd like to introduce my co-authors Chen Ping, Wang Jingdi, and Liang Zhiling from Beijing Normal University, and Liang Zhiling also from University of Maryland. The presentation is about the data-based stochastic assimilation method to estimate the time series LAI. I'd like to introduce our work in these 5 parts. As we all know, the leaf area index is a key parameter in crop growth monitoring and yield estimation. Recently, global LAI products are routinely produced from data acquired from satellites such as MODIS, Vegetation, AVHR, and etc. But due to the consistent crowd contamination, instrument problems, and retrieval algorithm inaccuracy, it often failed to get reasonable values in time series. There are ways to get time series LAI. The most popular way may be the data assimilation techniques. It couples the radiative chance model and the crop growth model. It can provide more information about the canopy's state variables in time and space. But it's very sorry to see that the need of large number of input parameters of crop growth model and the variation of land cover and surface inhomogeneous, this always can hamper the application of the model at a large spatial scale and limits the confidence in the output. Here we listed some types of parameters always needed in the crop growth model. They obviously including the genetic characteristics of the crop, the soil properties, the weather data, and the crop management information. Maybe someone think this is not so difficult to get, but when we use the model to global or regional usage, this 4 kinds of parameters is difficult to get in long time series and large scale. The second way to get the time series is the statistical models. I'd like to introduce the work of Zhou in 2010. She presented 3 statistical models to characterize the non-stationary time series data and to predict the future values. It's including the dynamic harmonic regression model, seasonal trend decomposition proceeding based on noise model, and the seasonal auto-regression integrated monitoring average model. These 3 models are robust in the time series LAI monitoring and prediction, but there are no theoretical guidance on selecting the parameters of these models. She just tried times and selected the best parameters in regional use. But if you want to get the long time and large scale use, it's always difficult too. The last method I want to introduce the database mechanical model. This is first introduced by Chen Ping in 2012. It extracted the relationship between the reflectance of observations and the LAI with a dynamic model, pixel by pixel. So the historical observation data of the pixel are needed. If you want to get the pixel value estimation, you need the historical observations of the exact pixel. So let's see, if you want to use this model, you need to get lots of historical observations, and the model construction work is very big. So the purpose of this our work is to propose a data-based stochastic assimilation method to estimate the time series LAI. The work including 3 parts. First is to generalize and simplify the LAI DBM model to regional scale. That's to say we want to construct a universal LAI DBM model. And the second step is to cover the canopy radiative transfer model. Here we use the process model with the LIU DBM model to estimate the reflectance with the current of the observation. And the last step is to take advantage of the ensemble comma filter to recursively update the LAI. That's the final LAI we get. Here I list the materials that we used in this work. First is for UDBM model. This is a universal DBM model, which means that we can use this model in a regional or global region. The data used for this model construction is the satellite model data of historical long-term modest reflectance product. Here we use the model 09A1 and the modest global leaf area index product sets. These sets are all the subsets from on bare manifold. And the data for for ensemble comma filter data assimilation scheme is the time series of modest reflectance data. Here the modest LAI product is not needed. But before used in the assimilation scheme, the reflectance data is under quality control. That's only the QC equals to 0 is used in this work. The data for model validation is we select 3 bare manifold sites. These 3 bare manifold sites are not used for the universal DBM model construction, and 2 big fold sites with the ground measurement used for the validation. These 2 tables lists the shows the detailed information about the sites selected for the model validation. Now I can give the details about our method. First is the LIU DBM model construction. The role of this model is to provide the LAI climatology or estimation background in this work. We just want to get the LAI climatology in the regional or global scale, and but the value is not the last estimation value. It is revised from the DBM model but has the same form with DBM. To simplify this, the model construction work, we select 20 sites of forest and 20 sites of other kind of site, land cover of bare manifold sites to construct the UDBM model. Here we make some simplification because we think that the forest sites has the relatively high LAI and the other sites has the relatively low LAI. So we just use this method to construct the UDBM model. The general form UDBM is like this. Here the LIT is the LI we want to get. Here it used as the climatology, and the R127 is the modest reflectance according to band 1, 2, and 7. Because these 3 bands are used for LAI estimation in Modi's LAI product, so we also use these 3 bands. And the B and A are the model parameters, and the L is the backward shift, which has the form of L like this. With this, we can simplify the formula as like this. So like this, so that if we can confirm the I, J, K, and N, so we can make the model constructed. So here, long time Modi's reflectance and the LAI model are used to train the model and get the B, I, J, K. The second step is to coupling the radiative chance model and the LIU-dBm model. The result of LIU-dBm will refer to LIU-dBm is input together with other state variables into the procedure to calculate the simultaneous bidirectional reflectance, which has the same angular information of the current observation. Because the Modi's reflectance data is used for the next step of LI estimation, but the Modi's reflectance have the different directional information, so we want to get the reflectance estimation with the same angular information of the Modi's reflectance. The state variables are sensitive parameters of procedure model, and the local sensitivity analysis method is used to make sure the state variables. Here is the parameters of procedure model. This is the local sensitivity analysis result. That's the local. When we do the local sensitivity analysis, only the parameter we want to confirm is varied and the other are confirmed. Because here are the Modi's band 1, 2, and 7 band response function. All the values are combined. First make a band composition with the Modi's band response function to get the value which is the same as the Modi's band. The final state variables confirmed are these 6 one. Here the LAI is, we just use the LIU-dBm model estimation as the LAI value for the next estimation. Finally, the ENKF assimilation method is employed to adjust the LIU-dBm to estimate the time series LAI. When the reflectance with current observation angular information is simulated, the ENKF operates directly on the model to get the estimated LAI and further to renew the state variable for next time estimation. Here gives the formula of ENKF. Here gives the flowchart of this work. Here the time series valence LAI and reflectance under SG field is used to LIU-dBm construction, and then the recent reflectance and the LIU-dBm method is input to the UDBM model to get into the UDBM model, and the state variables with the reflectance with the current angular information is input together to the procedure model and simulated the reflectance with the current directional information into the ENKF and then renew the estimation. Here we introduce the LUDBM model construction result. Here is the LUDBM1 for forest sites, which has the relatively high area level, and this is the LUDBM2 for other kinds of vegetation. Here indicates that the LUDBM, here is the blue dash lines, here means the LISG, and the red is the UDBM model result. Let's say the LUDBM can always get the LI barrier pattern of the forest, but in the other sides, here in these sites, the LI are relatively high, but the UDBM is fit not very well. Here we see the result compared with modest LI product in 3 biomanic sites. Here is the in Laris is a forest sites. We see that the modest LI fluctuates very much because of the missing of the observation, reflectance observation of the algorithm failure. But the UDBM can catch the normal LI variation pattern, and with the LENKF with the new reflectance introduced, it can get a much more reasonable value. Here is the inbound wear in the it's a crop site, and which has the similar results. And this is the shrub. Here we can see that because the shrub is not the forest site, so the UDBM2 model is used to get the LI climatology. So the UDBM estimation is cannot get the peak value of the LI, but with the new reflectance introduced, the estimation value is much more reasonable. So we can see that compared with modest LI product, the LI product fluctuates due to the missing of reflectance observation and the retrieval failure. But the LI-UDBM can represent the common variation of LAI. The ENKF data assimilation algorithm can efficiently modify the AI background to get a more continuous and reasonable estimation. Then we compared the value with the estimated value with ground measurement. Here the green dash lines means the LAI models, and the line we can see that the LAI ENKF value is much more closer to the ground measurements, and also in the next site. So compared with the ground measurement, we can see that LI-ENKF and the models are in very good agreement, and they are all very close to field measurement. But the LI-ENKF is relatively smoother. Furthermore, LI-ENKF is slightly better by the LI models compared with field measurement. But this work is just validated in limited sites, so we need more validation work. So it comes to the conclusion that we generalize and simplify the LI-DBM model to regional scale use. It can successfully depict the regional area dynamic. By using the LI-DBM model to supply area estimation climatology in the data assimilation sim, and last, the data-based assimilation method can submit in the crop growth model with a simplified model. It is proposed here. but we still need some improvement. First, the approach does not consider the bidirectional reflectance character of the ground when using the modest reflectance data for the UDBM model construction. It may be introduce some error for the original air background information. Some further work is focused on this aspect, and the second is the more validation work is also needed here. I'd like to acknowledge the projects supposed for this work. Thanks.